Hi, in this video we are going to talk about prime numbers, which is a very important part of number properties, which in turn is a very important part of your GMAT quant. This video will be about concepts and will be followed with many more videos on practice questions on prime numbers. Let's start the journey right now. Alright, so as I said, this one is on the concepts of prime numbers, then we'll have questions on prime numbers, but this here is a series on number properties. You're going to have a lot more content on the other topics in number properties, so make sure you subscribe to the channel so that you do not miss out on all the good content. Starting with prime numbers, what we have is a small recap of what prime numbers are. Here's the definition. A prime number is a positive integer that has exactly two different positive factors, 1 and itself. Now, every number in the world, every positive integer in the world does have two factors for sure, 1 and itself. If I take, say, the number 10, then 1 and 10 are two factors of the number 10, but it has more factors as well. 2 and 5 are also factors of 10. So it's not exactly two factors that 10 has. And for that reason, 10 is not a prime number. So remember, prime number should have only these two factors and nothing else whatsoever. So what do I call a number like 10, something that has more than two factors? Well, this is what you call them. More than two positive factors, such numbers are called composite numbers. Let me now give you some examples of composite numbers first. So you have 4, 6, 8, 9. Let's just discuss 4. So 1 and 4 are automatically two factors of the number 4. I don't even have to think about them. These are always going to be factors. But the moment I find one more factor, I'll be through. I'll call it composite. So I have 1, 4, and 2. Which means the number 4 does have more than two factors, and so it's composite. Similarly, you can check for the others. What about the number 1? Well, I've made a statement here. It's neither prime nor composite. Why? How many factors does the number 1 have? It has just one factor, which is 1 itself. And that is why neither does it fit here in exactly two factors, nor does it fit here in more than two factors. So it's neither prime nor composite. Because again, as I said, it has only one factor. Now these are some prime numbers. You can check any of them. They only have two factors and no factor other than them. Now notice one thing here in this very first prime number. This is an even number, while the rest of the list you see, it's only odd numbers. So a point here that we are making is that 2 is the only even prime number. All other prime numbers are odd. Why? Because any other even number in the world will have 3 guaranteed factors. What are those 3? 1, itself, and the number 2. Every even number is divisible by 2, right? So that is why we have no other prime number that's even. Another observation here in this list is in the numbers 2 and 3. Look at 2 and 3. These are consecutive integers. Consecutive integers, that means they come one after the other. You have 1, 2, 3, 4, 5. So 2 and 3 come one after the other. And they're both prime. They're both in the list. This, in fact, is the only pair of consecutive numbers that are both prime. So this is again a very important point. You will have no other consecutive numbers in the world that will both be prime. Now remember, there's a difference between consecutive prime numbers and consecutive numbers that are prime. Just see the play of words here and the meaning changes. Consecutive prime numbers just means prime numbers that come one after the other. So you have 2, then 3, then 5, then 7. So these are consecutive prime numbers, one after the other. While 2 and 3 are already consecutive numbers that are both prime. So be careful about this. Next now is a very important part in prime numbers, which is prime factorization. What is this? Every positive integer k, every positive integer can be expressed in this form, where p1, p2, p3 are all prime numbers, and m, n, r, the powers that you see here on top, are non-negative integers. Non-negative means they are not negative, so they can be positive or 0. Well, really, 0 is the only case when all the powers are 0. That's in 1. That means when the number whose prime factorization you're trying to write is 1. Because 1 will have to be written like 2 to the power 0, 3 to the power 0. If you take any other power, then it will not be 1. But for all other numbers except 1, these powers are going to be positive. This is prime factorization. So you break down any positive integer in the world, you can break it down into a product of its components. That is a product of its prime factors. Let's see some examples here. So 4 is 2 squared. What does this mean? 4 is equal to 2 times 2. Just see, 2 times 2 is 4, right? You broke 4 down into a product of prime numbers. 2 is a prime number. 8 is 2 cubed, which means 8 is 2 times 2 times 2. Again, I broke this down. Now in this case, what I had was both these numbers, 4 and 8, had just one prime number throughout. So just 2. But you could have more than one. So the number 6 here is 2 times 3. You have 2 prime numbers. 12 is 2 times 2 times 3. So that's why I've written that as 2 squared. Similarly, there are more examples for you to check and understand this. Now, after we're done with prime factorization, another important thing you have to understand is what happens if you do some things to your k, whose prime factorization you were trying to find out, and you want to see what happens to the prime factorization. How does it change? Let's see that here. Well, k is this that I'm starting with. Now what I'm doing first is I am raising k to the power a, where a is another number. I'm not saying an integer yet, remember. Now what happens as a result? This is something you know from exponents, that powers get multiplied. So this is p1 to the power am, p2 to the power an, and so on. Now notice one thing, the prime numbers, the prime factors that you have for k to the power a are p1, this one that's highlighted first, p2 and p3. These are exactly the same prime factors you had for k, right? So k to the power a has the same prime factors as k. So although your prime factorization changed, but the prime factors did not change. It's still the same building blocks for the number. Now what happens? Let's see in an example to understand this better. So you have k as 2, k squared is 2 squared. The prime factor is still just 2. Another one is this here. All you see because of k to the power 5 is that the powers have changed on 2, 3 and 5. But you don't just start getting new prime factors. It's just the same prime factors. Another operation we have is this, when we multiply something with k. So you're multiplying a to it. This is how the breakup looks, but I'm not really sure if a is in the prime factored form or not. Now I still see p1, p2, p3 the same prime factors as before, but I have no idea about a. And unless I know a, I can't give the exact prime factorization of ak. This ak may or may not have the same prime factors, so everything depends on a. Let's see this using two examples. This here, in the first example, you see k is 2 and I took 2k. So my a here is 2. That did not change the prime factors I had. It's still the same. But if k is this with prime factors 2, 3 and 5, and then I multiply a 7 to it, I'm giving it a new prime factor, 7. So in this case, they have different prime factors. So everything depends on the number that you multiply. While here we were sure that the prime factors are not going to change. Now with this, we have one last thing to discuss before we summarize everything. So here I've brought in a k with its prime factorization. We know what p1, p2, p3 are prime numbers, and m and r are non-negative integers. Now what I want is not the number of prime factors, because the prime factors would just be what? p1, p2, p3. I just have to count which ones I have. But here I want the total number of factors, not just prime. So for example, the number 10, I have to count 1, 2, 5, 10, not just 2 and 5. So that is what we have to do here. Now, do you really have to count everything manually? No. We have a very nice formula for this. total number of factors of a number k whose prime factorization looks like this is given by this formula. Now observe carefully how we're getting these things. This power m, we added 1 to it. This power n, we added 1 to it. And same thing you'll do to all the powers, and then you're just multiplying these numbers. Okay, so here's an example, 900. This is the prime factorization of the number 900. Think about counting the number of factors without this formula. It'll be 1, 2, 3, 4, 5. It'll take forever if you go on checking till 900. Thanks to this formula, we don't have to do that. All we have to do is increase each power by 1. So each power here is 2. When you add 1 to them, all of them become 3's. So it's just 3 times 3 times 3. 27 is the total number of factors. Simple. Now one step forward when you go from this number of factors thing is when you discuss even or odd factors of a number. So this is what we just saw. We saw that the total factors that it has is 27. What if I wanted just the even factors or just the odd factors? Think about odd factors first. Now if I want just odd factors, then 2 should not be a part of them, right? So 2 should be crossed out. I will see only those factors that are composed of 3 or 5. So you could have 2 3's, 2 5's, or just one of them to get all the factors. So just think about this new number that you have, 3 squared times 5 squared, and think about how many factors this is going to have. So you again apply the formula, but just on these 2 this time. So the total number of factors, odd factors, will be this 2 plus 1 and this 2 plus 1. So that's going to be 3 times 3, 9 odd factors you have. The moment you have odd factors, getting even factors is easy. Well, you had total factors 27, you had odd factors 9, so even factors are obviously going to be total minus odd. So 18 factors are going to be even here. So you see how this one formula you could use to create 3 kinds of questions. You could be asked the total factors of a number, or the total odd factors of a number, or the total even factors of a number. Every time you just have to think a little and apply the very same formula. Now with this, we're ready for the summary of the lesson. First was a definition of prime numbers, positive integer with 2 positive factors only. Then we talked about prime factorization of a number, that every number, every positive integer in the world can be expressed as a product of its prime factors. Then we talked about what happens if you multiply something or you raise your number to a certain power. If you multiply, ak may or may not have the same prime factors as k, but if you raise k to a power, it will have the same prime factors as k. Finally, we saw the total number of factors of k of this prime factorization. I'm sorry about the format. This is supposed to be powers m, n, and r. The total factors are m plus 1, n plus 1 times r plus 1. This is all we did, and as I said, we will be posting questions based on prime numbers. Make sure you attempt them and practice all that you learned here. There's a lot more detail in which I've discussed these concepts and done questions in a webinar on number properties. Please find the link to that here. Attend that to solidify your understanding all the more. To stay tuned, make sure you subscribe to the channel to never miss updates and find all of this content every time.